Good morning. In these sessions, we are going to discuss the third Maxwell equations. So this field equation relates the so-called electric field with the magnetic field. That means the space variation of the electric field is due to the time variation of the magnetic field. So that we are trying to understand from this particular. Okay. So before deriving this, we started from the idea of Faraday's laws of electromagnetic induction that you studied earlier. Uh, the magnitude of induced EMF is directly proportional to rate of change of magnetic flux. This is what the statement of the Faraday's law in electromagnetic induction. The magnitude of the induced EMF is directly proportional to rate of change of magnetic flux. So after that proportionality is removed by the minus sign, so we got this relation E is equal to minus d phi by dt. So this nothing but the induced EMF, phi is the magnetic flux, okay, is the induced EMF and phi is going to be the magnetic flux. So d phi by dt indicate the rate of change of the magnetic flux. So this is mathematically written, is stated like this: negative rate of change of magnetic flux, negative rate of change of magnetic flux across an open surface, this is important, is equal to the EMF induced across that closed path. So you imagine the just a ring, so that ring surface is nothing but the closed path. So if you are keeping the ring through the open surfaces, the wind can blow. That's what the idea of open surface closed path. Okay, it's after all a bangle, simple way. The bangle, that is a closed path. It contains the surface that is going to be the open surface. So then mathematical statement is this of the Faraday's law: negative rate of change of magnetic flux across a open surface is equal to the EMF induced across that particular closed path. Okay. So now this is an idea. Consider this open surface. This is the open surface. This, yes, bounded by a closed loop. So this is the closed loop. Okay. So this is the open surface. This is the open surface, closed loop. See. Okay. So here what we are observing is the magnetic flux through this particular surface, and the EMF induced here is represented at this particular point. Little clarity was not there. So this is the magnetic field crossing, the magnetic field crossing through the surface. This is the unit normal at this particular point. Okay. The magnetic flux through any surface, this is also you studied earlier, magnetic flux phi is equal to NAB cos theta. This is what you studied, or that is nothing but N stands the number, A stands the area, B stands the magnetic field strength, and theta cos theta. So instead of that we are writing magnetic flux phi is equal to A dot B. A stands the surface area, B stands the magnetic flux, magnetic field strength. So that when it is written in an integral form, the magnetic flux through this surface phi is surface integral of B dot ds. Okay. The magnetic flux through this surface is phi equal to surface integral of B dot ds, and this ds is written in terms of unit normal, a vector perpendicular to x, and this equation changes to this B dot n ds, where n is the unit vector normal or unit normal vector perpendicular to this surface. So this is the unit vector perpendicular to the surface. Okay. So this is what the magnetic flux linking through this particular surface written mathematically. Okay. As I said, using the Faraday's law, whenever there is a change of magnetic flux, an EMF is going to be induced. So this is what the change magnetic flux crossing this surface. The magnetic flux, if it is changes, an EMF is going to be induced. So the EMF induced across that closed loop is given by this E is equal to the line integral E dot dl. So this is going to be the induced EMF around the closed loop, okay, where E stands the electric field induced in the space, okay. So how it came? Whenever the magnetic flux changes, an EMF is going to be induced, okay. So magnetic flux across the surface we understood, that is B dot ds. So because of that, an EMF is induced across the closed loop, which is given by this, where E stands the electric field induced, okay. So this is the equations. So what I did here is, see this, in the place of E, I'm going to substitute, in the place of E, I'm going to substitute this surface integral, because from this particular idea, E is equal to surface integral B dot ds. So this place I changed it this, okay. So what is the meaning here? Clearly understood. This is the first part, the EMF induced. How EMF induced? Because of the change of the magnetic flux. Look at, this is the magnetic flux changed, hence an EMF is induced. And this EMF induced is also going to be this one. So induced EMF around the closed path is going to be this much. So what Faraday law said, whenever there is a change of magnetic flux, an EMF is induced. So this is EMF induced, and this is the due to the change of magnetic flux. So this left hand side are going to be same. So both indicates the change of the magnetic flux, reason for the EMF to induce. So now you can equate this. Why you can equate this? For the fixed surface, for the fixed curve C and the surface S, neither our S nor our C depends on the time. So this is important. And again, make it clear this one. How you got this two? This is also expression for EMF induced. This is also expression for EMF induced. It's a simple way. You know, electric potential is nothing but E is equal to dV by dx. Electric intensity is nothing but potential difference by length. So therefore the potential difference is what? Electric intensity into dl. So that way expression for the EMF induced. This is according to the magnetic flux change idea, the EMF induced. So both are one and the same, left hand side is equated. So I can equate it mathematically also. For a fixed surface C curve free and a surface S, the so-called S and C never depends on the time. So both S and C not depends on the time. Therefore, I can take this dou by dou t inside this particular. So that is a mathematical. Okay. So the rate of change, the size of the curve or the surface enclosed because of that curve. That means the bangle size is not changing. Therefore, the open surface is not going to be changing. So that is an idea. For a fixed curve C and the surface S, neither the S or not C depends on the time value not changes. Therefore, I can equate this first and I can take this dou by dou t inside. First I equated and then I took dou by dou t inside. Now, this is the Stokes theorem. Look at in the previous last part. It's a line integral E dot dl. It's a surface integral dou b by dou t dot ds. So this has to be equated. Either we should bring it to both the line integral form or the surface integral. That's why I'm taking the help of a Stokes theorem. Okay. So according to the Stokes theorem, the line integral E dot dl is nothing but the surface integral curl of E ds. So here you can write del cross E. That also you can write. So this is according to the Stokes theorem. So this previous term E dot dl now according to Stokes theorem becomes curl of E dot ds. Okay. So that is why this particular term del cross E dot ds on the left side and the right hand side dou b by dou t ds. So this equation is true for any arbitrary surface. So since this is true for all the arbitrary surface, so you can straight away in the place of E dot dl write this curl E dot ds according to Stokes theorem equal to surface integral minus dou B by dou T dot ds. So if these two, look at, both are the surface integral ds. So if you are equating, you are going to get del cross E equal to minus dou B by dou T. This is going to be the third Maxwell's field equations. Okay, look at this field equation. This side contains del, that means I dou by dou x plus j dou by dou y plus k dou by dou. That means it speaks up something about the space variations, space derivative. Look at this, it is going to be the time derivative. So what it relates here is the space derivative of electric field at a particular point is equal to the time rate of change of magnetic field at that point. What it says, at any point, if there is any change in the magnetic field with respect to that time, and at that point the electric field is produced, or the potential difference is established, or an EMF is induced. Again observe it, space derivative of electric field at a particular point is equal to the time rate of change of magnetic field at that point. That means whenever the magnetic field at any point changes with respect to time, then at the same point an electric field is induced, or a potential difference is established, or an EMF is going to be induced. So this is nothing but the generation of the, better word, this is nothing but the production of the electric field at a point due to the variation of the magnetic field. Or in short, you can understand, whenever the magnetic field changes, an electric field is going to be produced at the same point. Okay, that's what I have written here. Space derivative of E at a point, electric field at a point, to the time rate of change of V at that point, so that it relates. So from that, what we are understanding, generation of the electric field, the production of the electric field at a point due to the variation of the magnetic induction at the same point. Okay, so this is the nothing but the mathematical interpretation of Faraday's laws or the Lenz's law. Okay, so this particular equation, what you are seeing, the equation, it is a time dependent equation. Look, as here there is a t is there, time dependent equation, and also the space variation of E with the time variation of V, and similarly the relation between the electric and magnetic field can be understood from this particular point. Or in general, it is very simple. We know whenever the magnetic flux changes, an EMF is going to be induced. If there is an EMF, then a current can be established. If there is a current, then the magnetic field can be produced. Magnetic field is going to be produced. Or in short, there must be or there should be a relationship between the so-called the magnetic field and the electric field. So that's what we observed here. The space variation of the electric field is equal to the time rate of change of the magnetic field at the same point, or whenever the magnetic field changes at a point, at the same point the electric field is going to be produced. Okay, thank you. With this, I am going to stop today's sessions. In the next sessions, we are going to discuss if the magnetic field changes and electric field is going to produce, then the nature maintains symmetry. The electric field variation should produce the magnetic field. So that we will discuss in the next subsequent sessions. Thank you.